So hi everyone, welcome to the ICTS String seminar. Today we have Irene Valenzuela from CERN who will be talking to us about at the boundary of the Swampland. So over to you, Irene.
Okay, so thank you very much for the invitation and for coming to listen to the seminar. So my plan is to talk about some recent progress that we have made understanding the universal features that arise at the boundaries of the field space and how they relate to the Swampland program. So this is based in several works, mainly the last two with José Calderón Infante and Ignacio Ruiz, and with Miguel Montero and Cumbrón Baza. So the most important thing before I start is to remind you all that you should not hesitate to ask questions or interrupt me at any point. Sometimes it's difficult with the online talks to make them interactive. So please, I'm very happy if you just unmute yourself and ask whatever comes to your mind. Okay. So the main question that drives the Swampland program is, what is the space of consistent effective field theories weakly coupled to Einstein gravity? Okay, where consistent, what we mean is that they admit a UV completion in quantum gravity. Okay, it's the same type of questions that, for instance, you ask with the modular, with bootstrap in the CFTs, but applied to EFTs weakly coupled to Einstein gravity. Now, if you imagine all possible effective field theories, the point is that not everything is allowed. We are trying to determine which ones are consistent. And since we are talking about effective field theories, they naturally come together with some energy scale because they are defined always up to some cutoff. So the proper picture is not just to have these disks, but I like to put more like a cone in the sense that the constraints that distinguish what theories are consistent and which theories are not consistent is something that depends on the energy scale. It's something that depends on the cutoff in such a way that typically the larger the energy scale at which you want your effective field theory to be valid, the more constraining the more constraining is. Okay, and we say that those theories that are consistent belong to the landscape, while those that are not consistent belong to the swampland. Okay, so from the perspective, I mean, what we use is typically string theory as a laboratory to identify what these constraints could be, like what distinguishes the landscape from the swampland. And then once we identify patterns coming from string theory, we try to find what is the reason underlying those patterns and whether we believe that it's a fundamental thing of quantum gravity or just a technical thing of string theory. So from the perspective of string theory, when we talk about the space of consistent theories, the space of parameters, since there are no free parameters, since all the parameters are parameterized by the vacuum expectation value of some scalar fields, the question of where we are in this space of parameters is equivalent to ask whether we are in the field space. Okay, so what is the value, the possible value of the scalar fields that we can take so that we can move in this field space, in this space of parameters by changing these vacuum expectation values. Okay, so let's consider this field space, this string landscape possibilities, like different vacua coming from string theory. And then the question is, what distinguishes the landscape from swampland, from those theories that are not consistent? Now, we know very little about the middle of the modular space, but we know a lot actually, even in the absence of supersymmetry, we know a lot about the asymptotic regions. Okay, so what I mean is that once you have this scalar field manifold, you can define some metric, typically coming from the kinetic term, the scalar fields. And then you have regions which are at infinite distance in this metric. So these are the boundaries of the field space. And this is what I will be calling asymptotic regions. Now, these infinite distance boundaries of the field space are special in the sense that they they can be understood as different perturbative descriptions. So when you have some scalar that goes to infinity, you can use this scalar field as an expansion parameter. Okay, so the point is that you can always do some like Taylor expansion, some expansion, and perturbative expansion around the infinite distance boundary. And if this scalar is parameterizing, for instance, some gauge coupling, what happens is that the gauge coupling goes to 0, and these are like weak coupling limits. Okay, so we have some expansion parameter. It could be a gauge coupling or not, but the point is that there is an expansion parameter that allows us to have computational control of the theory, even if we don't have supersymmetry.
Question.
Yes.
So I'm getting earlier, but I hope you're going to define how you define the metric on the field space, right?
Yes. This is just like general to put a bit the state of the art. Then we'll go to concrete setups, and then you can see, I mean, exactly how we define the metrics, depending if it's in the bulk or even we will define it on the CFT as well. But basically, so you keep something in mind. The point is that you have to go. So this is effective field theory is weakly coupled to Einstein gravity. So you have to go to the Einstein frame. And then it's like in physics terms, it's like measuring on the canonically normalized field. So you just have like the 1/2 derivative of the scalar field square. And this is the geodesic distance in the modular space, which geometrically will correspond to the Weil-Petersson metric in the modular space and so on. Okay. But yeah, it's important.
So you're saying the kinetic term defines the metric? Kinetic.
Exactly. So in practice, what you can keep in mind is that you have all your scalar fields, you have some kinetic terms, and the field metric, right? Like you can define a metric from the kinetic term, which is a metric on this scalar manifold.
Okay.
And then you measure distances using that metric. Okay. Which in physical terms is like saying that you canonically normalize the field in Einstein frame. But there is a very geometric picture. Okay, we'll see. Okay, and if you have more questions, you can ask again later on. Okay. So yeah, so we'll see from a geometric perspective of the string theory landscape where we have scalar fields, no, parameterizing all the internal dimensions and so on. We can define some metric, and these are infinite distance boundaries. From the point of view of the effective field theory, these are like we have some expansion parameter and we have some sort of weak coupling or perturbative limit. And therefore, whenever we have these weak coupling limits, what happens also is that these regions, what we have in these regions are sort of approximate global symmetries. Okay, because when, for instance, a gauge coupling becomes very small, you are going to restore some U1 global symmetry. So these are some special regions in that sense. Okay, so the point, what we will see in this talk is that in these asymptotic regimes, when we go to these asymptotic regimes, there are some universal quantum gravity features that emerge that typically are promoted to these Swampland constraints. Okay, so what we will see is that regardless of what is the asymptotic limit that you take or what is the compactification manifold, it seems that there are some features that emerge all the time. And the goal, I mean, with the Swampland program is trying to understand these features and why it happened, no? What is the underlying reason? Whether is it necessary because of quantum gravity consistency or what's going on? Okay, what happened with these universal patterns? So let's start. So what I'm going to do first is to tell you what these universal features are. Okay, and what are the Swampland constraints that they are related to. So there are many more Swampland constraints, but I'm just going to focus on what happens on these asymptotic regimes. Okay.
Sorry, Irene, a question.
Yes.
When you say regardless of which asymptotic limit you take, you mean regardless of which infinite distance point you go to?
Mm-hmm. Yes.
Okay, thanks.
Yes, exactly. So that goes very. So this is this change of paradigm from the Swampland program respect to the usual stream model building, because the point is that instead of trying to construct the specific vacuum that describes our universe or try to understand exactly where we are, what we try to identify are universal patterns that appear all the time, and use them and study what are the implications of these universal patterns. Okay, so what are these universal patterns that I'm going to focus in this talk and that are important right now? Okay, so first of all, whenever we go to some infinite distance singularity of the moduli space and one of these boundaries, in all the string theory compactification that have ever been studied, there is always an infinite tower of states that become exponentially light in terms of the geodesic distance. Okay, so if you are at some point in the modular space and you travel to some, approaching one of these limits, the effective field theory close to the limits differs from the previous one by containing this infinite tower of states, which decreases exponentially in terms of the geodesic distance that you travel in the field space. And this is very natural from string theory because it's one of the first things that you study, in the sense that, for instance, if I think that this scalar field is some volume of the internal dimensions, then what I get is that when the volume goes to infinity, I decompactify the theory and I get Kaluza-Klein towers becoming light. Okay, so this is just one example of this. But also what you learn in string theory is that when you send the volumes to zero, you also get like winding modes, like wrapping strings, wrapping branes that become light. And they also satisfy this. And the fact that you always get these towers are the protagonists, are the stars of all the dualities that are known in string theory, like T-duality, S-duality, and so on. So also when you take a string perturbative limit, like S goes to zero, you get string modes. So whenever, the fact that we always get some of these dualities emerging at the infinite distance limits happens because we get this new weakly coupled description of the theory given by this infinite tower of states.
Sorry, how do you define delta phi? What is the definition of delta phi?
Yeah, so delta phi is the geodesic distance. So, as I said, once we will make it concrete and we take the metric, so you can define a metric on the scalar manifold using the kinetic term, and then you can study what are the possible geodesics. And if you fix 2 points, like I have 2 points in my scalar manifold, the mass of the tower will behave exponential in terms of the geodesic distance of a trajectory, the shortest geodesic connecting the 2 points.
And why is that related to the volume of the internal space?
Because this is just one example. Like imagine that the interpretation, the microscopic interpretation of this scalar field is some radius, it could be in string theory. You can ask what is the microscopic interpretation once you have some string theory embedding. And one example is that when you have, since in string theory you can start from 10 dimensions and compactify to lower dimensions, the volume of the internal dimensions is parameterized by the vacuum expectation value of the scalar fields. So you can choose one scalar field which parameterizes some volume of the internal dimension, and therefore if I send this delta phi to infinity, I send the radius, I send the volume to infinity, then I will get the Kepley tower. So imagine that you have a cycle compactification, so it's easier, like from 5 to 4 dimensions. It's a one-dimensional modular space. Any trajectory then is a geodesic, and this delta phi is just the radius of the internal circle. Okay. More questions? Very good. I like that there are questions. So let's continue. Okay. Okay, so far it's very general because I'm not telling you what is the delta phi. It can be whatever in your effective theory and can have different microscopic interpretation. But yeah, I just wanted to remark that when you just check string theory embeddings, we see it's very natural because you always get towers of states when you change, when you go to these boundaries, because it's what defines all these string dualities. Now, the other feature, well, let me maybe say one more thing. So it's natural from string theory, but why we are interested in this is because it's very surprising from an effective field theory perspective. Because in principle, there is nothing wrong with having a large variation of a scalar field, as long as all the energy scale remain below the cutoff. And what this is telling you is that by quantum gravity consistency, it seems that the cutoff in the field variation is correlated to the cutoff in energies, because you get new towers of the states. So we'll see this in more detail, but that's why it's interesting. Now, the other feature I'm going to focus, and then we'll go into more detail in each of them, is what happened with the scalar potential. So imagine that now I have a scalar potential for these scalar fields. So is there any universal pattern that arises when I go to infinite distance? So the answer seems to be yes in string theory. So whenever you go to these boundaries, I will tell you the evidence later on, it seems that the scalar potential always has like a runaway behavior to 0. Okay, so if it's positive, it just continue running without inducing any minimum. And this is what sometimes was also known as the Dinosaur Problem, but generalized to any field distance. And I call it asymptotic, the Sitter conjecture, although it doesn't have a very well-defined name, because it's like what these people define the Sitter conjecture, that the potential, the gradient of the potential over the potential has to be bigger in some order 1 factor. And this is precisely saturated by this exponential behavior. And it's something that seems to happen asymptotically. Yes, please.
Maybe you'll explain this later, but is there any particular reason why we should be interested in the asymptotic regions?
Yes, so I will. So, yeah, 2 things. First, asymptotically, the advantage of the asymptotic regions is that you have some computational control, so you can derive what is the effective field theory that you get from string theory. Most, if not all, the string theory model building that has been done, it's always in some asymptotic regime because of this. So if you have supersymmetry, a lot of supersymmetry, you can determine what happens in the middle of the field space. But in the moment in which you try to connect with the real world and break supersymmetry, we only know what happens asymptotically in general. Now, this is just a technical thing, okay? Like this when where we know how to compute things. But then at the last part of my talk, we will discuss how well the features that arises asymptotically describe our universe. So whether we could live in an asymptotic limit or not, and what motivates us to think that maybe we live in an asymptotic limit. Okay.
Okay.
So far, it's just a matter of characterizing, okay, what happens there, because it's where we can compute things. Okay. Okay. So these are 2 universal features that we will, these are the 2 features that we will discuss during the whole talk. Okay, I just wanted to put them in front from the beginning. And they are promoted to Swampland constraints because, these are patterns that arise from string theory, but they are very universal. And we believe that they are necessary by quantum gravity consistency. Now, the whole goal, the game now, once you identify the pattern, this is just the first step. All the work comes on proving this, right? Like you have to find more evidence in string theory, understanding what is behind, and also look for bottom-up arguments independent of string theory to explain why this should be the case. Now, one of the most important things is that here I just told you that there is a tower that decreases exponentially, the mass of the tower decreases exponentially, and also the potential decreases exponentially, but I didn't say anything about what are the exponential rates. So in this conjecture, these exponential rates are 3 parameters, okay? They are supposed to be order 1 parameter, but it's not specified what is the value that they can take. And this is very annoying because if we don't give the exact value, it's very difficult to give any phenomenological implication or to make this something concrete and precise. Okay. So a lot of work in the past few years has been gone into determining, like trying to understand better what these values are and how to compute them in general. Okay. And this is good because, I mean, I think at the moment, so a few years ago, we just wanted to check the exponential behavior. Now we are really determining and fixing what these values can be. And I think we are entering into what I like to call an era of precision in the Swampland program, in the sense that we have so much data now of studying this in string theory and ADS-CFT and so on, that we are ready to ask exactly what these values are, like more refined questions, and fix all these ambiguities that sometimes are related to the Swampland constraints. And this is very important both for phenomenology, as I will tell you, but also from a pure theoretical perspective, because like understanding what these limits are, so what are the possible values, what are the possible limits that I can have, is equivalent to classify the possible quantum gravity theories. Because what happens in these limits is that, I mean, of course, I'm gonna get like some singularities and infinite number of states become light, but quantum gravity always have a way to resolve this. And the possible resolutions, the possible type of limits tells you, like what are the possible quantum gravity theories, quantum gravity resolutions we could have. For instance, to make it more concrete, if this corresponds to the compactifying, then I know that one resolutions is grow extra dimensions. So I know that quantum gravity can have extra dimensions. If one resolutions are string perturbations, string modes, I know that quantum gravity contains strings. So like understanding how the effective field theory breaks down and what is the quantum gravity physics that emerge give you information about the quantum gravity completion. Okay, so let me just quickly tell you what are the important phenomenological questions that you could answer if you know exactly what these values are. And then we will move to understanding the evidence behind this conjecture, precisely more concretely in the context of string theory and ADS-CFT. Okay, so just quickly, so for the infinite number of states, so the point is that if you get an infinite number of states becoming light, the EFT is going to break down because you cannot have infinitely many fields quickly coupled to Einstein gravity. So there is an associated quantum gravity cutoff to this tower. And that's why I was saying that this conjecture is relating the cutoff in energies to the cutoff in the field space. And in practice, if you want to have an effective field theory which is valid up to some cutoff lambda, the field range that you can describe within the effective field theory is upper bounded by this. Okay, so this is what the conjecture is telling you. And this is what happens in all these string theory examples. Like whenever you try to have a very large field range, since you get this tower of states becoming light, the cutoff goes to 0, and then the field range is bounded. Now, in order to say exactly how much is bounded, it's very important to know this exponential rate. Okay, so for instance, you can try to apply this to inflation and put bounds on the field range, because then this is going to put bounds on the tensor to scalar ratio that you can measure. But how much, I mean, what are the exact values, again, will depend on the exponential rate. So it doesn't make sense to start talking about the phenomenological constraints unless we really fix what this value is. And second, for the scalar potential, so the point is we have this runaway behavior. So you could ask, okay, can I use this runaway to describe some accelerated expanding cosmology? Okay, because on one hand, it's nice, like the potential is positive. So even if it's not a vacuum, I can have a quintessence model, so like a time-dependent vacuum. And in principle, this can also describe some acceleration. But the point is that having a positive energy is not enough. It is enough to have expanding cosmology, but not accelerating expanding cosmology. So even if it's nice that since the potential goes to 0, it's nice that at these asymptotic limits, actually the vacuum energy becomes naturally small. So that's something very suggestive for our universe. We really need to require also that the slope of the potential, so this exponential rate, is not too large. Okay, so
Question.
Yes.
So this cosmological constant can also be treated as a module like?
Say again, sorry.
The cosmological constant can also be treated as a moduli in this paradigm.
Yeah, exactly. So it's like you have some potential for some scalar, and it's a runaway so that you have a time-dependent solution. And then it's like the cosmological constant is not a constant, but it's running. No? It has some time dependence. And this is what are called these quintessence models.
No, so I was wondering why you can't also incorporate the acceleration of the, the change in the acceleration by, tuning the cosmological constant.
With tuning, you mean like changing the shape of the potential so that the slope is
Yeah,
large?
just as this the scalar has a certain say potential, maybe the cosmological constant would also have some sort of potential in which it.
No, the cosmological constant is the value of the potential, the potential energy. So yeah, so I'm thinking, so when you have the, right, like this is the, if I think of the cosmological constant is going to be the energy of our vacuum, right? So if this is potential is the potential for all the scalar fields I have, the vacuum, no, the smallest value is what would correspond to the cosmological constant. So it's the value of the potential energy. It's not something extra that you can tune.
But then you also have to take into account the vacuum energy of the various fields. I mean, how do you?
Yeah, exactly. So this would be the final potential. Okay, exactly. So right now I'm just putting one scalar for simplicity of the slides. But in general, you have all your fields in your theory. You compute the scalar potential for all the fields, and the vacuum, right? The smallest energy is what gives you the vacuum energy. Now, this is this is what happens in gravity. Like in quantum field theory, it doesn't make sense to talk about the absolute energy. But when you have weakly coupled gravity and you have the potential, then you can talk about what is the vacuum energy for taking into account the potential for all the fields that you have. Yes. So yeah, when you try to describe in string theory some model that describes the accelerated expansion of the universe, what you have to do in practice is to compute the scalar potential for all your fields, and then check what is the vacuum energy. And this will tell you what is the value of the cosmological constant.
Okay.
Okay, but yeah, it's all the fields. Okay. Now, the point is that we can do this. I mean, that's why these asymptotic regimes are useful. Because in the asymptotic regimes, we can compute the scalar potential and we can check what is the result. Okay, so on one hand, why it's difficult, maybe you have heard it's difficult to get string theory, the sitter in string theory and so on, is because we want, when we have the runaways and we want to generate a minimum. So generating the minimum, like stop the runaway, it's hard and people are working on it. But right now I'm trying something even simpler in the sense of, we know, like from string theory, I will show you that we always have this runaway, that for sure we can compute the value. So can we, instead of trying to generate a minimum, try something easier, which is at least see if this runaway can describe some asymptotic acceleration.
Is there any way to get graceful exit?
Graceful exit? Well, if I use the runaway, then this is going to continue running forever. That's why it's
I mean from the initial inflationary phase. From the initial inflationary phase, can you get a graceful exit through these potentials?
For inflation, it's not so useful. That's why I said quintessence. Like for inflation, it's not so useful to use these runaways because they just continue running forever, and then it's difficult to talk about reheating and many of the other things, like to exit inflation. That's why people, when try to do inflation, you try to do it like deeper in the bulk or add other things. So like you cannot just continue asymptotically. Or at least, I mean, it's not the easiest thing. I mean, people are trying, but it's not the easiest thing to do. But like, as I said, like right now it's a zero order question. Like I'm not even going to ask what's the end or how to end it. I just want to know if it's even possible to have the accelerated expansion. Okay. And whether it's possible or not depends exactly, again, on the value of this exponential rate. Because if this exponential rate is too large, this does not describe acceleration, it's deceleration. So it has to be smaller than the square root of 2 in 4 dimensions to describe acceleration. Okay, so everything comes down again to determine what are exactly these values.
No, I'm just concerned about whether there is any way to get from the initial inflationary phase where you have a much higher rate of inflation to the current rate of inflation in any way through these methods.
So the current, you mean like the current expansion of the universe?
Yeah.
This is more about model building. I mean, I don't have a specific model in mind now that can accommodate both things. So this is, as I said, it's like a next order question. Okay.
Maybe a comment. It's not necessarily the same field, right? Which is responsible for inflation.
Exactly. It's not the same. Yeah,
So
yeah.
Maybe that can answer the question.
Yeah, exactly. So here I'm just putting one because it's easier to draw it. But in general, you're gonna have many scalar fields, and then you're gonna have some trajectory on this field space that can involve many fields. It's like a much more complicated question, no? Like what I mean, like how to make a model with that describes the full cosmology evolution of the universe, and then have one trajectory in some scalar field, and maybe it goes asymptotically to another one, and so on and so forth. So I'm not going to do a phenomenological model right now for our universe. I just want to understand whether asymptotically, like parametrically, at parametrically late times, quantum gravity and string theory can describe acceleration or not. Maybe it can describe it earlier, like for a short time, then wondering now what happens asymptotically.
Okay.
Okay. So what I'm going to do in the rest of the talk, so I have told you about these universal features. So now we are going to make it more concrete. So I'm going to tell you what we know about this in more detail. So first, what is the nature of the tower of states in general? And what are therefore the implications? And what is the evidence both from top down and bottom up that we have? And then I will focus on this asymptotic accelerated expansion and try to determine, what is the value of the slope to see if asymptotically string theory can describe acceleration or not, regardless of whether we can use it later for our universe or not, but at least whether it's it's something useful to understand also what is the fate of asymptotic observables in quantum gravity, because if we can have acceleration, then that gives us a lot of information. If we can show that we can never have acceleration at parametrically late times, then it gives us information about whether we need to have always some asymptotic observables, some mismatrix description, and so on. So we'll check this, and I will finish the talk with some comments about how to apply this for our universe. This will be at the very end. And how, if we happen to live in an asymptotic limit, then we need to have this tower of states, and therefore we can give some sort of universal prediction, which is a light tower of states of order neutrino scale. So we'll see this at the very end. Okay, so let's go into more detail. First, asymptotic towers of states. Now, this is something that we've been testing for several years now in state theory. We have followed a systematic approach, classifying the possible infinite distance singularities that you have in these field spaces, depending on the level of supersymmetry. And at the moment, we have very good understanding what happened with theories with more than 4 supercharges. And now we're trying to reduce supersymmetry. Now, the take-home message that I want you to take is that from all these many works, from all these works, more that I'm not citing here, the conclusion is that all limits seems to be either the compactification limits, so that in some dual frame, so that when you go to this infinite distance limit, you grow some extra dimensions, or string perturbative limits, in the sense that you get some tensionless string. So not tensionless membranes, tensionless strings. And whether this is the only two possibilities is what these people argue. That should be a general feature, and that's what they call emergent string conjecture. Now, it's nice that if these are the two only possibilities, the exponential rate that we compute in all these examples, Calabi-Yau compactifications and everything, always fits into this formula, in the sense that if it's the compactification, the exponential rate is associated to a Kaluza-Klein tower, so it depends on the space-time dimension of the EFT and the dimension of the higher dimensional theory. And if it's a string perturbative limit, it depends on the space-time dimension of the EFT. So you can completely characterize what is the exponential rate and use this then to put precise bounds on the field range that an effective field theory can accommodate. Okay, so this is all for flat space compactification and Minkowski compactifications. So this is Minkowski effective field theories. But we also studied what happens in ADS, okay? Because then we can translate this to some statement on the CFT that we can aim to prove using CFT techniques. So from when we have an ADS background, we can also have some flat space direction, some massless scalars, and this modularized space translates in the CFT to the conformal manifold, to the space of exactly marginal couplings. So the field metric that was given in terms of the kinetic term, I should have actually written it now, I'm sorry I didn't. Well, this field metric, this kinetic term, will map to the Samologikov metric in the conformal manifold, which is given by this 2-point correlation function. And the tower of light states will map to a tower of operators situated in the unitarity bound. So what we propose is that there is always some infinite tower of operators that are actually higher spin operators whose anomalous dimension, which will be equivalent to the mass, decays exponentially in terms of the Samologikov metric when you go to infinite distance in the conformal manifold. Okay, so this is the equivalent statement of the distance conjecture, but from a CFT language.
Question.
Yes.
In what sense does the Samologikov metric define a distance in fields in the conformal field space?
It does. So people have shown that this Samologikov metric, it's a metric, it's positive definite, it satisfies the triangular inequality, and defines a metric in the space of exactly marginal couplings. So it's the natural metric to use in the conformal manifold.
What are the TIs?
Here, TIs would be the different marginal couplings.
Okay.
Okay, and O would be the marginal operator.
Left hand side there is no TI. Okay, in any case. How are the TIs defined in the left hand side? How are they incorporated in the left hand side?
Yeah, this is because here I chosen. This is very sorry. This is inherited from for n equals 2 or n equals 1 that you have supersymmetry and these TR complex fields. So I was just calling T like the complete field that defines, and XY will be just some points. So you have some correlation function, and that is computed at some point X, some point Y. You have your CFT defined on these points, and then you have you can relate the two CFTs related by this marginal deformation that is parameterized by the complex field, which I call T.
So this correlation function in general would depend on the interactions you are saying. So that's why it would depend on the couplings. The correlation functions.
Exactly. Yeah. Exactly.
The correlation functions, they would depend on the interactions which are involved.
Yeah. So, for instance, if I will show you in the next slide, but an example of a marginal coupling is a gauge coupling. And then the operator, the marginal operator, is the trace of F square, of the field strength square. And therefore, when you take the 2-point correlation function of trace of F square,
it would depend on Gy.
Exactly. Okay. Okay, so so why we have this proposal is because when you go, I mean, all the known examples in support conformal field theories of infinite distance limits correspond to 3 points, corresponds to weak coupling points. So the example I just told you is not just one example, it's all the examples we know are of that type, in the sense that the marginal coupling is a jump Mills, some gauge coupling in the CFT. And the infinite distance point occurs when the gauge coupling goes to 0. So it's a 3 point. Now, 3 points by Malasenas y Boedov, they show that 3 points always have some higher spin symmetry. So that if you have a 3 point, you are going to have a higher spin tower of operators. And therefore, you can just also prove the other way around, so that if you have a higher spin theory, this is going to be a 3 point, so the gauge coupling goes to 0, and then you can show, we show in the paper that this is at infinite distance in the Samolov-Zhukov metric. So the only part which is not proven, and it's still an open question, is whether the only way to go to infinite distance is to have a 3 point. It's not, is the case in all the examples, but would be nice to have a general proof.
So by higher spin tower, you mean higher, more complex operators in the Yang-Mills theory? I mean, what do you mean by higher spin towers?
I mean a tower of operators that has spin bigger than 2.
Okay, fine.
So that in the bulk would correspond to some fields of higher spin, that like spin bigger than 2. Okay. So okay, why? So how we can prove this? How we can prove that weak coupling, like these 3 points, are always at infinite distance is because since the gauge coupling is going to 0, you can just use perturbation theory. And as I said, the marginal coupling is just given by the trace of f squared. So you can just compute the 2-point correlation function and so compute what is the metric, this Samolov-Zhukov metric. And all the coefficients, everything is determined and will depend on the dimension of the gauge group. That is associated to the gauge coupling going to 0. Okay, that is getting free. So what is the conclusion of this? Is that if we have a weakly coupled ADS dual, this CFT, then it implies these 3 points imply that there is always a tower of higher spin fields at infinite distance with an exponential rate that is completely well defined, and we compute that is given by the ratio of the central charge over the dimension of the gauge group that is getting free. Okay, so this is just, just wanted to give you the result to be able to go to other things. But this is very nice because it means that it's automatically lower bounded because the dimension of the gauge group can never be bigger than the central charge. And we can also take this formula and compute it in examples and see what are the possible values that we get. Okay, so we did this in the paper, and just to give you the conclusion, from all the possible simple gauge groups that you can have in 4 dimensions, n equals 1, n equals 2, or n equals 4, when you compute the exponential rates using this formula, there are only 3 possibilities that arise, which are these 3 numbers. And now you can ask, okay, do I have an interpretation of these 3 numbers? So we could try to compare with the results that we got in Minkowski. Okay, so in Minkowski, I told you that it seems that everything is always string perturbative limit or the compactification limits. So the exponential rates are also fixed. Here, I'm telling you that all these limits are actually sort of string perturbative limits because you always get this is a higher spin tower. So it's like if you have a string becoming tensionless in the bulk and you have all the higher spin excitations. Now, this is a puzzle I wanted to share with you. I don't have an answer for this yet, but it's funny that even if they are all higher spin limits, the exponential rate doesn't match with what you would expect from the critical string, which maybe makes sense because we are in IDS, and this is, this result of 1 over square root of 3 is derived in supergravity, and this is going beyond supergravity. So maybe the ADS scale is modifying this, but it would be nice to understand how. But what is more funny is that these 3 numbers, it's a coincidence, maybe, but it happens to match with what a Kaluza-Klein tower the exponential rate of a Kaluza-Klein tower decompactifying to 8, 9, and 11 dimensions. So I mean, this is something I'm trying to understand better. I'm sharing this with you just in case, I don't know, like it's also sometimes here you find people that are experts on these tensionless string limits and so on. If anyone is interested or has an idea, I'm happy to discuss further. So I like to share my puzzles with the people because sometimes this way you can also find nice collaborations when giving talks.
Sorry,
So,
to understand the thing better, I mean, you are saying that the alpha for n equals for various supersymmetric theories, the alphas are defined as in the first line, whereas in the string perturbative limit, do you mean they have supersymmetries as well?
So I'm saying that from the CFT perspective, you can compute what is the exponential rate, and you get these three values here. So that's the result that you get from CFT. Now you want to give it an interpretation from the bulk perspective, from the ADS.
Yeah.
And then we know that these are towers of higher spin field. So the natural thing would be that they should be related to string perturbative limits. But instead, the exponential rates that we get are what one would get from the compactification. But in principle, there is no decompactification here because I just get higher spin fields. So I don't know if somehow maybe what happens is that there is some decompactification in some dual description, which is not known yet, or the sigma model of the tensionless string describe more dimensions. So just to give you one example, for instance, the 1 over square root of 2 is what happens in ADS 5 crosses 5, in 4D n equals 4 super Yang-Mills. So if you take n equals 4 super Yang-Mills and put GS to 0, you have this tensionless limit. In the ADS 5 crosses 5, you have the fundamental string becoming tensionless, but still the exponential rate that you get is what would be equivalent to have a Kaluza-Klein tower decompactifying to 11 dimensions, which in principle have no sense, makes no sense, because we are not in 11 dimensions.
Oh.
So why you have this numerical coincidence is an open puzzle right now. Okay, more questions?
So maybe I have a question here.
Yes.
So I wonder, like, for example, in this ADS 5, in these tensionless limits, do you expect that there are something like this transition happen there? Because you have this infinite tower from massless space, and I guess maybe they get condensed, right?
So it's a limit in which some string becoming tensionless, but also weakly coupled. Okay.
Right.
So it's not like a strongly coupled behavior. And then, yeah, it's like sending GS to 0. And then what I expect is that, yeah, like what QFT doesn't work anymore. Like I have some string theory description, right? Like I should have some sigma model for this tensionless string. And I don't know more about it. Like I don't know what happens. I know we know how to compute it from the CFT, but from the ADS dual, you go beyond the regime of validity because you go to highly curved ADS space, which is of order the string scale, and you get this strings.
Yeah, but just in this particular example, like this ADS times S5, the field theory I think is 40 and equal 4, right? And this tensionless limit, this tensionless limit is corresponding to this free super Yang-Mills limit, right?
Yes, exactly. The free limit.
And I guess that there's some paper done by a Bo. I can't remember the authors, but they said there's a Hagedorn transition.
It's a higher transition because you get all these higher spin fields, right? Yes.
Right.
But the question is whether, yeah, like, is this higher transition somehow sensitive to more dimensions, and that's why this is matching, or what's going on? That I haven't seen in any paper.
Okay.
Okay, so let me speculate a little bit. I mean, for n equals 4, you usually have SO6 R symmetry, and that corresponds to an S5, right? So when you have n equals 2 and n equals 1 supersymmetries, I suppose they would correspond to SO some other gauge groups, which would correspond to lower dimensional manifolds, internal manifolds, instead of the S5, say S3, or suppose it's S3, then D equals 8 would correspond to that, right? I mean, because ADS5 and S3 would correspond to 5 plus 3 is 8.
Let me say, so these three values are not n equals 4, n equals 2, or n equals 1 supersymmetry. Okay. You can find gauge fields also in n equals 2 and n equals 1 that have the 1 over square root of 2, and like it gets mixed. There is not a clear pattern there, so that I can see so far. I mean, there should be a pattern, but I don't know. It's not just related to the level of supersymmetry.
So
I thought maybe to the R, the R symmetry would be nice, because sometimes the R symmetry you have to the geometric perspective, you need more dimensions. So that's one way of thinking, but I couldn't make it work yet.
But then what do these 1 over root 2 and root over 7 by 12 and root over 2 by 3 correspond to, if they don't correspond to n equals 1, n equals 2, and n equals 4?
So from all the possible groups, we computed the numbers, and you get, sometimes you get one, you get the other, or the third one, like regardless of if it's n equals 1, equals 2, n equals 4, but it's always these three. So there should be something. Is it like a new way? I mean, I think this can, I mean, in flat space, we use this to classify possible limits. I think in the CFT can be used as a new way also to classify these possible CFTs, that somehow they should be related to each other, even if they share different level of supersymmetry. So they all fall into these three possibilities, but I don't know why one or the other one. It's a matter of what is the portion of the gauge group that gets free in comparison to the central charge.
No, but for SUN Yang-Mills with a in the large n limit, the different n equals 1, n equals 2, and n equals 4 theories would correspond to certain numbers, right?
So there are many. You have
theory,
many within n equals 1, equals 2. You have many possibilities. It's not just one.
No, for the Yang-Mills, for SUN Yang-Mills, for instance. That's
SUN. Yeah, SUN. Then you just have 1 over square root of 2.
You just have 1 over square root of 2, regardless of the n, of the number of supersymmetries?
Yes, I think so. Yes, I think so. Yes. And also only when I take different gauge groups that I get the other values. I can show you, there are some tables, I think in the backup slides, I have some tables with the results. So I have each gauge group which corresponds to, so I can show you later if you want. Okay, maybe let me proceed because I'm running out of time. So this is, it's one puzzle to discuss. As I said, I mean, sometimes people tell you that you should not talk about things that are not clear yet, because then people start working on it, but I'm very happy to continue discussing and generate discussions with people around the world. So let me know. Now, I think I'm gonna skip this because I'm running out of time. I just have a few words about some bottom-up evidence that we try to argue for the existence of the Tower of States in terms of finiteness of black hole entropy. So it's just because if you have small black holes, you can engineer a very large field range in the space-time, and you can show that this would be inconsistent with Bekenstein bound unless the effective field theory breaks down precisely as dictated by the conjectures. But maybe let me skip because we are running out. You can ask me later during the questions. And let me say a few words, at least, I mean, a bit more about the scalar potential. Okay, so as I said at the beginning, so let's consider we have some effective field theory that is weakly coupled to Einstein gravity, and we have all the kinetic term for our scalar fields. So this capital G is the metric, okay, that we were using in the field space, and we have some scalar potential. Now, to get accelerated expansion, the scalar potential needs to satisfy, when we have this runaway, needs to satisfy that the exponential rate is smaller than this square root of 2. Okay, so this is what I told you at the beginning of the talk. Now, the goal now is to determine what this value is in the same way that we have done with the exponential rate for the Tower of States. Okay, so for the Tower of States, we already have good description of what are the possible values depending on the limit. In Minkowski, everything works. In the CFT, there are still these open questions of understanding the meaning of it. But we have these classifications. Now, the goal is to do the same with the scalar potential. They have a classification and understand whether we can have a value which is smaller than the square root of 2, so that we have acceleration asymptotically in string theory or not. Now, there are some proposals about what this value should be. So it was proposed by Conrun and Alec that is always lower bounded by this value that depends on the dimension of the space-time. And Tom Rudelius recently proposed this other bound, which is stronger, because precisely it would imply that the runaway behavior can never yield accelerated expansion, because he proposed that this gamma is always bounded by square root of 2. Okay, so my goal in these papers was to check this in string theory to understand whether this proposal is satisfied or not. Okay, so the goal was to understand whether we can have asymptotic accelerated expansion in string theory. Now, for concreteness, I have focused so far, for the potential, we don't have so much data as we have for the tower of states yet. So I have focused on 4D=1 effective field theories. Okay, so supersymmetry will be broken by the positive energy, but of shell, I have a 4D=1 theory. Okay, now, first of all, so it was proposed by Tom Rudelius in this paper that even at the level of supergravity, one can have accelerated expansion, which was very strong. And what we have done is also to show a loophole to this argument. So just quickly, because I don't have much time, the point was that if you have 4D=1, you can derive the scalar potential from some superpotential. And then if you have this exponential behavior, and you assume that also the superpotential has this exponential behavior, then you can relate the two exponential rates, so that when you compute the scalar potential, the exponential rate of the scalar potential enters here. And if you want the potential to be positive, then this puts a bound on the exponential rate, so that you cannot have accelerated expansion. Now, what we have seen and we have shown an example is that this correlation between the exponentials is not always true, because precisely when we have more than one scalar field, because then the gradient flow trajectory can be different for the potential and the superpotential. So this argument is not true in general. Okay, so the question is, can we put a bound? I mean, if this argument doesn't work, can we still put a bound on this exponential rate, on what I call the de Sitter coefficient? So maybe how much time do I have?
How much time do you need actually? Is still fourth, maybe half 15-20 minutes is okay?
Okay, yeah. If you allow me 15 minutes, then I can finish everything.
Sure.
Yes. Okay.
Yeah, sure.
Okay, then let me explain you this. So since sometimes computing this gradient, this exponential rate can be very complicated, what we did is to translate it to a geometric statement, like a pictorial picture, which allows us very easily to determine if a given scalar potential can yield accelerated expansion or not. So the point is that if you have some scalar potential, which is a sum of different contributions, the full gradient of the potential will satisfy this lower bound, okay, this way. If the different gradients of the different terms, like what we call this de Sitter ratio, so the derivative of the potential over the potential for each individual term. So if the convex hole of these de Sitter ratios lie outside the ball of radius C. Okay, so it can seem a bit confusing, but the point is that you have some potential with different contributions. The recipe is you compute what is this the derivative of the potential over the potential for each of them, this gives you 1 point in this space. You compute the convex Hall of all these points, and the distance to the convex Hall is the final, the Sitter coefficient, the final exponential rate of the potential. So if you want this exponential rate to be bigger than some value C, what you need is that this convex Hall lie outside the ball of radius C. So this is just a pictorial way to compute in general what can be this exponential rate and to provide bounds for it. So let me skip this. Okay. So the point is that there are two possible scenarios. One is when a single term dominates, or when several terms dominate asymptotically. Okay, so that the distance is not well, it's just in the segment. Okay. So the take-home message is that this second scenario is very important, because this second scenario actually can violate any of these bounds. Because as you can see pictorially, even if you have a bound for the individual terms, okay, so they are bounded, and one uses the argument of Thorne-Ruderius to bound each point, still it could be that the convex Hall cuts the ball, okay, such that the value of gamma, of the exponential rate of the potential, is much smaller than what you would get for each of the terms. Okay, so this is just to show you that we show that in general there is no lower bound for this gamma for the n equals 1. So in principle, you can make it as small as you want by even if the individual terms are bounded. Okay, so you just have to get this convex Hall closer to the origin. Okay, now still this is without putting any specific constraint on the overall shape of the convex Hall. So the conclusion is that there is no obstruction to get asymptotic accelerated expansion in supergravity, despite these no-go theorems that were formulated before. But you can still ask, okay, what happens in concrete examples? Can you find a concrete example in string theory that realizes this or not? So what we have done is to check large classes of examples. Let me put here the full slide. So what we have checked are F-theory compactifications on Calabi-Yau force with the goal of studying different limits in the modular space. Okay, so the point is that what people have done so far was just to study what happens on one particular infinite distance limit. So I told you there are many types of infinite distance limits, right? One of them is what people know as the weak coupling large volume limit. And this is what most of the works are always done. But this is just one type of limit. And if we want to give general constraints that are universal for all possible limits, we need to study what happens in other limits. And this is what we have started to do in these papers. So we have, in the context of Calabi-Yau manifolds, we can go to different limits in the modular space and study precisely what is the flux potential and what would be the value of the exponential rate and everything, and see what happens. So let me just show you the results. So yeah, we can just classify the scalar potential. So I have here how to classify geometrically. These are like tables of the possible scalar potentials you can have and different infinite distance limits of the field space. Only one of them corresponds to GS going to 0, like the weak coupling limit, like perturbative string theory. All the others are not perturbative string theory, okay, but still are infinite distance limits. And you can compute what happens in all these cases, and the result is that we find two examples which a priori could yield accelerated expansion and therefore would violate previous bounds. So these are two concrete examples that we found that violate these bounds because the gamma is smaller than square root of 2. And it's very important that they were realized in this scenario 2, in which there are several terms that compete with each other. Okay, and it's a smaller value than what has ever been found in the literature. Now you could say, okay, so are you telling us that you have shown that there is some accelerated expansion in string theory? The answer, unfortunately, is still not clear, not yet, because there are still other moduli in the compactification, like Keller moduli, that we have not stabilized yet. So one should then stabilize the other moduli, and only then we can have a full model and be sure that we have accelerated expansion. Okay. Any question about this?
I have a short question.
Yes.
How robust are these results to say corrections coming from gravitational instantons, for instance, like non-perturbative effects?
So because the point is that when you go to the infinite distance limit, precisely what characterizes the infinite distance limit is that you have some expansion parameter in the sense that the non-perturbative corrections are suppressed. So the farther you go into the asymptotic regime, the more suppressed the corrections are. Because this is a result for, I mean, this is the advantage, like this is like parametrically controlled. It's not just numerically controlled, it's parametrically controlled. Like you can get at infinite distance as far as you want and completely suppress all these other corrections. So that's that's why it's robust in that sense. The caveat is that in these examples I'm showing, not all the moduli are stabilized yet. So this is something that has to be done first.
I see. Thanks.
Any other question? Okay, so this is, so these are first works to try to determine what are the possible values for the gamma, if it can be too small, and whether string theory allows for accelerated expansion, even if it's time dependent. Okay, asymptotic alerts. Okay, so just to finish the talk, I'm gonna make, I think 5 minutes is enough, and I finish. I want to combine both things. Okay, so this was just, at the moment, it was more like a matter of classification. What can happen asymptotically in these asymptotic regimes, how fast the tower of states decay, how fast the potential decays, and so on. But now the question is, can we use this for our universe? Okay, can we live in an asymptotic limit? Okay, so what would make us think that maybe we live in an asymptotic limit? So what properties of asymptotic limits resemble our universe, and which ones do not? So first of all, as I said, these asymptotic limits are sort of weak coupling limits in a sense. Like there is some parameter that becomes small. Okay, doesn't mean that everything has to be perturbative. Like you have many fields, so it could be that you are at infinite, a large field distance in one, but not another one. So you have some perturbative, some small parameter, but others are strongly coupled. I mean, not everything weakly coupled, but at least you have one which is weakly coupled. That's for sure.
Question.
Yes.
Could you say that the neutrino masses come about in this fashion because they are asymptotically small?
That's a good question. So yeah, so it's one option. So I was gonna say, so in our universe, I mean, even if not everything is weakly coupled, we have some weakly coupled things, right? Like standard model, we have small parameters that sometimes we don't know how to understand. We have light states, right? Like fermions are light in comparison to quantum gravity scale. And this is something that typically you could argue, okay, maybe you can have fine tuning of things so that you cancel things and you get small numbers. But asymptotically, since everything becomes, I mean, these parameters become small, naturally, you don't need to fine tune anything. It's just that naturally, because you are in an asymptotic regime, you have some parameters that go to zero. And this can force you to have light stuff and weakly coupled stuff. So it's one, I mean, this one possibility. Okay, it's one scenario that this is the reason. And I like to mention this.
In any case, fermions, the fermion masses are protected. I mean, you don't, I mean, renormalization doesn't drive their masses to Planck scales. But,
so actually, no. So there is always this law that chiral symmetry, no, for protect the fermion masses to remain light. But in this paper, Razamat and Tom, they show that chiral symmetry is not enough to protect fermions to remain light if you are at strong coupling. So if our standard model of particle physics, if the Gates coupling for the electromagnetism was much stronger, then even if we have chiral symmetry, there could be non-perturbative effects that create a gap spectrum so that the fermions would be heavy. So this tells us that we have to be a bit at weak coupling. Like, that doesn't have to be parametrically weak coupling, but if it was not weak coupling enough, then the chiral symmetry wouldn't be enough to protect the fermions. So,
does that mean that inside the hadrons or the baryons, the quark masses are not light
it
enough?
means that if you really want to be in the middle of the modular space, it's very hard to keep things to be light in general, because everything naturally becomes of order the cutoff, regardless of chiral symmetry. Or
but quarks are light inside hadrons, right? I mean, quarks don't run away to Planck scale masses, right?
I'm thinking of electron, more about the electromagnetism part, because for QCD,
no, electromagnetism, the coupling is small in any case. I mean, it's not strongly coupled, it's weakly coupled. You're saying that Tong's result applies for strong coupling. Isn't that right? That's what you said.
Yeah. I'm just saying if it's strong coupling, then things could be.
Yeah. So I would suppose that they would apply for QCD. So the stuff inside baryons.
Yes, but then they check, these people check in the paper that the specific values of the gauge couplings in the standard model are still small enough such that these effects do not happen and things become light. So you can check the paper, it's very nice to see. So it's like in general, you don't have an abstraction, but the specific value that we get in the standard model still allows you to have light things. Okay, more things. So these are just like properties that maybe are easier to get asymptotically, so to motivate us why we could live asymptotically. Another thing is that asymptotically we get approximate global symmetries, and our standard model, for instance, have B minus L has approximate global symmetries. So that also suggests that maybe we are in some asymptotic regime. It's just a suggestion. And also, as I was telling you, when we are in these asymptotic limits, quantum gravitational effects become important at scales much below the Planck scale, because we get these towers of states becoming light, that become light exponentially. So the cutoff, the quantum gravitational scale, the quantum gravitational effects become important at a scale much below to the Planck scale. And this is actually an opportunity, because it could be that, I don't know, some of the naturalness issues that we observe in our universe have a quantum gravity origin, in the sense that quantum gravity becomes important in the infrared if you are in this asymptotic limit. So what I want to do to finish the talk is to argue or to think with you whether, in particular, the cosmological constant problem could be a signal that we are in asymptotic limit and could be resolved precisely because of that. Okay. So, as I said, imagine, let's suppose now that we are in asymptotic limit. It doesn't have to happen, it's just a scenario, okay? But imagine that we are in asymptotic limit in the string landscape. It could be that we are in these runaways, or maybe we manage to generate a minimum, I don't know, whatever, okay? I don't want to think of a particular model. All I know is that regardless of how we get the accelerated expansion, we are going to have this light tower of states if we are in an asymptotic region. So you could ask, okay, if we live in an asymptotic limit, what is the tower of states in our universe? Okay. So from all the string theory examples we know, and all the examples we have checked before, I show you from F theory, Calabi-Yau compactifications, all the examples, the potential, okay, the potential energy, which would be the cosmological constant, is correlated to the mass of the tower of states becoming light, because both decay exponentially. So in the end, you just have if they have different exponential rates, you can just write a polynomial relation between both of them. Okay, so the potential goes as the mass of the tower to some power. This is what happens in all these limits, because both decay exponentially. Now, you can try to bound what is this power. Okay, and we have bound exponential rates for both quantities, so we can now bound the ratio between them. And generally, also, you can bound from general principles, saying that, okay, at least they should satisfy the Higuchi bound, because if I have towers of higher spin fields, then the mass of the tower has to be bigger than the Hubble scale, so this is bigger than 2, and should be smaller than the space-time dimension, because at least if I don't have supersymmetry, at least I'm going to have quantum corrections, like Casimir energies, and these are going to give me this type of behavior. So at least I will have this power. So alpha has to be smaller than me. And the string theory examples that we know satisfy this. Okay. Now this implies that, okay, let me say, so this is interesting because if we are in an asymptotic regime, then the value of the potential energy, since it's correlated to the mass of the light tower, is much smaller than the Planck scale, and therefore goes against field theory expectations. So even if we have very heavy stuff, in the end, the potential energy is very small because it's going to zero. So it's not that you have a fine tuning of things, it's just naturally when you take into account the full theory and integrate out the infinite number of states and everything, the full string theory embedding, you see that the potential energy is very small. And it's purely a quantum gravity thing that you cannot do in QFT. Okay, so it's a possible scenario that the smallness of the vacuum energy is not due to a fine tuning of contributions, but it's a signal of being near an asymptotic limit where it naturally goes to zero. And then if that happens, if we, in some scenario, if we live in a asymptotic regime, then you should also have a light hour of states with a mass that is correlated to the cosmological constant in this way, because that's what happens in all these examples. And if we combine this with experimental data to see whether this regime is still allowed or ruled out or what's going on, we can see that most of this regime, this theoretical regime, is ruled out. The only possibility is that we are close to saturate this upper bound, so that the mass of the towers is of order the cosmological constant to 1/4. Okay, so combining both theoretical bounds and experimental bounds, one could conclude that the tower of states becoming light, if we live in an asymptotic regime, should scale as the cosmological constant to the 1/4. And this would imply, and combining with experimental data, we can show that the only possibility is that this signals only one extra dimension of order the micrometer, okay? Because the cosmological constant is very small. So then the extra dimension is quite large. And this is what we call the dark dimension. And this you could say, okay, but what happened with this tower? This is super light. I mean, it's a tower of order cosmological constant. I cannot believe that this is not ruled out already experimentally. Surprisingly, and surprisingly to me, it's not ruled out experimentally. So this is a tower which would be start at the neutrino scale, would be like a Kaluza-Klein tower of some extra dimension. And so far, all the bounds coming from astrophysical bounds and also deviation of Newton's law and all these things still allow for a tower of order neutrino scale. So it's one possibility. The conclusion, the take-home message is that if we happen to live in a asymptotic regime, then we should get the tower. So if we don't find the tower, probably it suggests that we don't live in a asymptotic regime of the moduli space. But then it's very difficult to get weakly coupled things. So one should rethink about all the string model building that has been done so far.
Question?
Yes. And these are the conclusions. So maybe let me conclude, okay, and then we can just ask all the questions. So just since I ran out of time, let me just flash the conclusions that we have studied these features that asymptotically these features are known as Swampland constraints because we think are general for quantum gravity. And we are now at the moment of making these constraints very precise and understanding all these order one factors to be able to give precise phenomenological implications. And one of the implications that we will have this light tower of states if we happen to live in an asymptotic regime. So thank you very much for your attention. And now I open for questions.
Are there any questions?
Yeah, I have a question. Like if you have a dark dimension of say of order of magnitude 10 micrometers, then everything, all fields should have this Kaluza-Klein tower, right?
No, not necessarily. So it could be, for instance, you have the standard model living on some brain, right? Like some stack of brains. These are localized in 4 dimensions. And then you have extra dimensions So you have some, in addition to the standard model, you have some Kaluza-Klein tower that have a different scale. So let me say, so if I have more, in addition to these large extra dimensions, if I have more dimensions that are small, up to 10 dimensions, then everything will have a Keiki tower, but the scale of the Keiki tower is very different to the scale of these extra dimensions. It's a different dimension. It's a different dimension. So the proposal is that there is the Kaluza-Klein towers of the standard model are much heavier. It's of order 10 to the 19 GeV, or like very heavy. But still we have some extra dimensions in which the standard model fields do not propagate. And we have the Kaluza-Klein tower of this extra dimension, which is of order the neutrino scale. So the neutrinos would be the only ones that are sensitive to this extra dimension, like right-handed neutrinos.
The neutrinos would propagate in the extra dimensions. Why would the neutrinos propagate in the extra dimensions?
It's like, okay, all we can say, I mean, all the universal thing is that you would have, in addition to the standard model, you would have some towers and Kaluza-Klein tower of states whose mass happen to be of order the neutrino scale. Now, it's suggestive then to identify it with the neutrinos. Okay, that's not something universal that we can say happens for sure. It's just that the tower of states happen to be of order the neutrino scale. And then you can ask, okay, can we identify this with the neutrino somehow, because it's the same scale? And it's possible to think that the active neutrinos is just like the zero order modes, the lightest one of the towers, but then you have right-handed ones that propagate in the extra dimensions. Right-handed neutrinos are sterile particles. They are not charged under the gauge fields of the standard model. So it's like having extra neutral particles that do not interact with the standard model, only gravitationally. And you can call them sterile neutrinos if they have at least some Majorana mass with the left-handed ones. But that would be the only interaction.
Usually the way the fields are restricted to the brane are if they're open strings, right? And one says that closed strings can propagate on the extra dimension. So
no. It would be, you have the open strings, like the standard model open string living on the branes. And then in addition, you have closed strings like Kaluza-Klein towers in an extra dimension. But this Kaluza-Klein tower can have a Majorana, can get a Majorana mass with the neutrinos, with the active neutrinos. So there are models like, for example, Nimark and Hamed, all the people from large extra dimensions have in the past have worked on models trying to have this, in which you have the Kaluza-Klein tower and then the standard model living on the brane, and how they interact gravitationally, and how you can have even Majorana masses between the two.
I'm just hard put to imagine that you can have left-handed neutrinos which are open strings and right-handed neutrinos which are closed strings.
It's possible. You can engineer the couplings to do it. I mean, calling them right-handed neutrinos, there is nothing special to those closed strings, just that the wave function of the Kaluza-Klein overlaps where the brane is located, so it generates a mass, like has some mixing between some of them. So something you can engineer, but all the fields that are charged under SU2, they are just localized on the brane. They are just open string. But I can show you. There are some references of papers that make this more explicitly.
Also, this cosmological value of the lambda. I mean, if the ultraviolet cutoff is at the is at the level of the cosmological constant scale, that is not at the Planck scale but at the cosmological constant scale. That's what you're saying, right? I mean, so the Planck scale just decays to the cosmological constant scale.
No, the Planck scale remains higher. So
I mean that there is an exponential damping term which takes it to the.
Yes, exactly. So exactly the quantum. So it's like that. Not two scales. No, you have the Planck scale, which is 10 to the 18 GeV, but the quantum gravity scale, where quantum gravitational effects become important, there is an exponential drop off, and it's much lower. the exact value, so I can put it here. So it would be, in this case, it would be 10 to the 10 GeV. So you have the mass of the tower, then you have the scale at which quantum gravitational effects become important, which is associated to, it's called the species bound, and then the Planck scale. So the quantum gravity scale is not of order the neutrinos, it's higher than that. Yeah, so it's something general. Whenever you have the tower of essays, I didn't discuss it because it's difficult to cover everything in 1 hour. But when you have a tower of states, like a Kaluza-Klein tower or StreamMOS or whatever, you have a scale which is the first, the mass scale, like the first state of the tower. But then you can ask, okay, what is the scale at which QFT breaks down? Like quantum gravity becomes important because I have too many fields coupled to Einstein gravity. And this scale is different than the first one of the tower. It's called the species scale, and it's above that, and you can compute it exactly what it is. And it's still exponentially smaller than the Planck scale, but higher than the lightest mass of the tower.
Are there any more questions? If there are, thanks, Irene, for the nice talk. So we'll meet next week.
Okay, thank you very much.
Thank you.
Thank you, Irene. Bye.
Thank you.